Hi everyone, in this video I'm going to just go over the first question in the Cantor Set project. So this question will have you kind of go back and use our knowledge of sequences, in particular geometric sequences. So we had looked at just how to list the terms of a geometric sequence and how to find the nth term of a geometric sequence. Remember that a geometric sequence is built by starting with some first term and then multiplying by some number over and over again to generate the remaining terms of that sequence. Imagine taking a geometric sequence and taking a part of the term or all of the terms of the sequence and adding them all together. So that's what we call a series. We have a formula to help us find partial sums, or S sub n, and infinite sums, or S sub infinity, of the terms of a geometric sequence. So here we have a new formula. The S just stands for sum, N stands for the number of terms of that partial sum. A sub 1, 2, 3, and so forth represent the terms of that geometric sequence. And if we want to add together the first n terms, instead of just listing them all out and then adding them together, there's a formula that we can use. This formula uses the first term, a sub 1. It uses r, the common ratio. Remember, that's the number that you are multiplying every single time. And it uses n, the number of terms that you're adding together. If we have a special kind of geometric sequence where r in absolute value is less than 1, so just think about a number between -1 and +1 on the number line, but not equal to 0. So if we have that case where r is some sort of fraction less than 1 or a negative fraction between -1 and 0, then the terms, each term of our geometric sequence is going to get smaller and smaller in terms of absolute value. So if we took all of the terms, an infinite sum, S sub infinity, and added them together, it will, what we call, converge to a particular number. The sum is not going to keep growing bigger and bigger. It's going to grow a little bit every single time, and then eventually it's going to grow so little that the sum will approach some particular value. And if we want to find that particular value, we can use this formula. So we're going to explore that in this first part. So you're given a geometric sequence, you're given the formula for the nth term, so we're going to use this formula. So nth term is generated by multiplying 7 times 1/2 raised to the n minus 1 power. So the first thing we're going to do is just use this formula, list the first 3 terms of the sequence, then we will find the sum of the first 7 terms by using the formula that you see here. And then we're going to find the infinite sum of the terms of the infinite series by using the formula that we see here. All right, so here I just rewrote that information. So your sum of n term formula is here. The infinite sum formula is here. That's only for when r is less than 1 in absolute value. And this was the term, the generator that we are looking at. All right, so the first thing we're going to do is find a sub 1. And I just need to move my controls out of the way here. Let me move this. All right, so to find a sub 1, that means we're going to go to this formula and replace n with 1. So we have 7 times 1/2 to the 1 minus 1 power. 1 minus 1 is 0, so that gives us 7 times 1/2 to the 0 power. 1/2 to the 0 is 1, so there we have 7 times 1, which is 7. That means our first term is 7. To get our second term, we're replacing n with 2, so 7 times 1/2 to the 2 minus 1 power. 2 minus 1 is 1, so we're multiplying 7 times 1/2 to the first. 1/2 to the first is 1/2, so that gives us 7 over 2 in fraction form. For our third term, 7 times 1, excuse me, that should say 1/2. Pretend that's a 1/2 to the 3 minus 1 power. So it's 7 times 1/2 to the second power. 1/2 to the second power is 1/4. And 7 times 1/4 is 7/4. And again, that is 1/2. I just wrote it incorrectly. So our first three terms are 7, 7/2, 7/4. And that would keep going. Every time we continue to multiply by 1/2, the numerator is going to stay the same, 7, but the denominator is going to get bigger. It's going to double every single time. So the next term would be 7/8, and then 7/16. And once we get to that next term, that fourth term, 7/8 is now a value less than 1. So the next thing we're going to do is find the sum of the first 7 terms. You could think about maybe the first 3 terms right now. We have 7. 7/2 is 3.5. So the sum of the first 2 terms would be 10.5. 7/4 would be 1.75. So we add that on. So the number that we're adding on every single time, it gets smaller and smaller. Okay, let's scroll down a little bit. So let's see the calculation for finding the sum of the first 7 terms. So using the formula above, S sub 7 is equal to our first term, 7, and we're going to multiply that by 1 minus r. R here is 1/2. That's the common ratio that we're multiplying. And we're raising that to the nth power. Since we're finding 7 terms, n is 7. And then we're dividing that by 1 minus r, which is 1 minus 1/2 in this case. All right, so let's simplify this. We need to raise 1/2 to the 7th power first. So our expression is now 7 times 1 minus 1/28, 1/128, divided by 1 minus 1/2 is 1/2. Now I'm going to simplify within the parentheses, so I'm subtracting 1 minus 1/128. I'm rewriting 1 as 128/128. So I don't have to even go to my calculator there. I want to keep everything in fraction form as long as possible. 128 minus 1 is 127, so that difference is 127/128. And that's over 1/2. Now I'll multiply 7 times 127/128. Multiplying a whole number times a fraction, I'm really just multiplying 7 times 127. When I multiply 7 times 127, I have 889. And the denominator is still 128. And again, I'm dividing that fraction by 1/2. When I divide by a fraction, I can change to multiplication of the reciprocal of that fraction. So I have 889/128 times 2/1. And I could simplify that a little bit. 2 and 128 are both even, so I'll divide by 2 and then multiply straight across. I have 889/64. Now this is in fraction form, that's the exact value. If I want to get an approximate idea of how big that is, it'd be about 13.89. So if I add the first 7 terms, so if I continued this list and added the next 4 terms and added them together, I would have a value approximately equal to 13.89. So it didn't grow very big from our original number 7. So if we were to continue this list infinitely and wrote out all of the possible terms out to infinity, which is impossible to do, we can though add them together because our r is small. Every time we're going to add a little bit, add just a little bit, add even less every single time. So this sum, if we calculated the sum of the 8 terms, sum of 9 terms, sum of 10 terms, and so forth, we're going to see that this doesn't really grow that much at all. So let's see what happens if we continue this out to infinity. So our formula for the infinite sum, S sub infinity, is equal to the first term, A sub 1, which in our case is 7, divided by 1 minus r. R in our case is 1/2. Again, this formula only works if the R is less than 1 in absolute value. 1 minus 1/2 is 1/2, so I have 7 divided by 1/2. And 7 divided by 1/2 is the same as 7 times 2, which is 14. So this means that if we were to list out infinite terms of this form, 7, 7/2, 7/4, 7/8, 7/16, 7/32, and so forth, and I added them all together, my sum would never go above 14. 14 would be where this sum converges to. All right, so you are using that in this first question here, but then you'll also use this formula later on when you get to the 4th page, I believe. Question number 3 of part 2. So you're going to list the expression in the previous question. So once you get here, this will make more sense. So list the expression as a geometric series. So write out the terms that you have so far. The R will be something that is less than 1 in absolute value. And then you're going to find the infinite sum of the series. So you're going to use that formula for infinite sum, like we did in that very last step of the first question. You're going to use that formula here.